I'm Peter Milne from Adform. You can tell by the dialect of English I speak, I'm not American, I'm not British, I'm Australian. So please forgive me if I say shit or fuck, okay? I'm a technology architect at Adform. You can see me down there. You find me on Twitter at HeliPilot50, and you find me in GitHub at HeliPilot50, suggesting to the fact that I actually am a helicopter pilot. But that's another story. What I'm going to talk to you about today is a little bit about Adform because marketing want me to. Then I'll tell you about high load, what the definitions are, some aspects of advertising technology, the DSP, the DMP, some of our DevOps, what we're doing with .NET Core, some data storage, how we use it, and then finally some Uncle Pete's advice. Okay, so this is the marketing slide. These are the three dudes who started Adform 15 years ago. They were hacking in a basement together, buying second-hand computer equipment to serve ads digitally. And that's where the business started from and has grown today. Look at this video for a minute. How many people did you see? A lot. I guess about 200. That's a 10-second video. That's Shinagawa Railway Station. I took that video while I was waiting for my colleague. Shinagawa Railway Station is one of the largest railway stations in Tokyo. They have 12 transport gates. You know the thing where you put your card down and the gate opens and you walk through? So when you enter a certain portion, when you leave a certain portion, you touch your card. Each one of those cards is an event that later becomes billing for you and money for Japan Railways. So, if you've got literally millions of people passing through those gates in a day, there's literally millions of events. And it's a good way to visualize high load. So I want to go through some definitions. So velocity, we always talk about velocity. In computer science speak, latency is velocity. It's how long it takes to get a particular piece of work done from start to finish. We have latency in our networks. We have latency in the I/O bus in the computer. We have latency in the persistent storage, whether it be a spinning disk or an SSD. We have latency in the actual time it takes to compute things or to select which core a thread is going to run on. So the whole latency is a sum of a bunch of individual latencies. Okay, so throughput is scale. So scale is throughput. They are both interchangeable. So you can think of throughput as the rate of production. It's similar to the formula for power. So power is work done over the time taken. So you can imagine that's exactly the same as how much work you can do in a certain period of time. So the power of your system is proportional to its throughput. So this is my first joke. You know the English expression that knowledge is power and time is money? So if you substitute that into the equation, then you rearrange the equation, you'll work out that the more knowledge you have, the less money you make. So that's what you look when you look at the salespeople in your organization. I'm sorry, it's a bad joke. So what's availability? Availability is always on. In the old days, before there was mobile phones, you used to pick up the telephone and there was always dial tone there. It was always there, regardless of the time of day or the number of people using it. So we think of that like the telephone. We like to have electrical power all the time. When you turn on that switch, you want the power to be available. These two are quite important. When you turn on the tap in your bathroom or your kitchen, you would like some water to come out of it. And when you flush your toilet, you would like that stuff to go away. So, which is more important, water supply or sewer? Consider this. Would you prefer to die because you couldn't drink or because you couldn't poop? Let's put that in a modern context. We think that Twitter's always available, or that Snapchat and Instagram or Facebook or Netflix are always there. So in our technological game, what do you do to provide always on? How do you build into your systems high availability? Okay, so there's some concepts I want you to think about. First area of ad tech I want to talk about is real-time bidding, and I'll explain what it is, then I'll tell you how we do it. If you go to your favorite website, so we've got Stack Overflow here, you'll find that that website is sponsored by an advertisement. And that advertisement tends to be something that you're interested in. It might not be anything to do with Stack Overflow or the subject you're looking at. You might be interested in cats, trips to Barbados, or new shoes, and you'll find an advertisement in that space that you're interested in. So what happens is the publisher of the website publishes this space like a billboard. They sell that space to somebody who wants to advertise. It's called an impression. When you click on the URL to go to Stack Overflow, a message is sent to an ad exchange where an auction occurs and people bid to display an advertisement in front of you. So advertisers pay for the privilege to put the ad in front of you, and the exchange decides who's paid the most amount of money and who's going to put it there. Okay, so that's real-time bidding in a nutshell. So there's a couple of sides to it. So I just showed you the sell side, or the publisher, where the publisher says, I've got a website, I've got some space to sell, I want to be sponsored. But it's not only a website. In your phone, you have apps where you get advertisements. And they usually, the application is free, and you can use it, but they give you an option to get rid of the ads where you buy your way out of it. The reason things are free on the internet is because they're funded by advertising. Just like free-to-air television is funded by advertising, same thing applies in the internet. So that's the sell side. That's what a publisher does. So if you want to make this really cool website and get somebody else to pay for the hosting and things like that, you could put advertising on it. On the demand side, this is where we, Adform, and lots of other people receive a bid request. So there's an auction going on in the exchange, and we bid on it. So we get some information about you, like the cookie or the IP address that you have or something like that. And we go, we know this guy, or we know this girl. We don't know your name. We don't know your telephone number. We don't know where you live, because that's illegal in Europe. It's not illegal in China. There's a whole pub discussion we can have later on about advertising in China. It's a different discussion. But here we just have an idea of what you're interested in based on your internet history. Don't worry about those questionable websites that you may have visited in the privacy of your own room. Everybody does, so it's just noise. So we build a profile about you, and we decide that you're interested in cats or shoes or new cars, and we find one of our advertisers who wants to place an ad in front of you, and we bid to put the ad in front of you. So we pay some money. We offer to pay some money on behalf of the advertiser. This all happens in about 75 milliseconds. So we get a bid request, and we want to respond to that bid request in about 75 milliseconds. If we go over 100 milliseconds, we've lost our chance. Okay, so we don't make any money, our advertisers can't spend their money, and they get grumpy with us. So how big is all of this? So that's one of our Grafana graphs. So this is the value of the market at any given second. So we store essentially 8 billion cookies or 8 billion IDs that represent you. We do the best we can to match your phone and your tablet to your IP address or the cookie. We have this cunning algorithm invented by some of our data scientists that are really cool and fantastic and smart people, and they do it for us. We're up all of the time. In fact, we can't go down. If we go down for an hour, it costs us around 200,000 euro to be down because we're not bidding. This is an old number. This is 1.2 million bid requests per second. We're maxing out right now, just before Christmas, at 1.5 million bid requests into our servers every second. So I said the bid latency, we've got 50 to 70 milliseconds we want to get things, make a decision on. We bid only on about 30% of the requests that we get. We don't care about the other, 70%. So the way we do this is we have a smart filter. And by the way, the smart filter was worked on by our engineers exactly here in Warsaw. They have an Nginx plugin that they take input from data scientists and they built it. So we can filter out the 70% of bid requests we don't care, so we can take more traffic. Built here in Warsaw. We win about 8%. 0.8%, I beg your pardon, on what we bid on. So just make that a 1. And we still make money. So at any one point in time, there's about €1 million worth of real estate advertising billboards to be sold in the market at any one point, any second in time. And we spend on behalf of our advertisers about €1 million per day. So we don't get €1 million per day, otherwise we would all be driving Tesla S's and living in some rich place, flying in private jets. We don't make that kind of money. But this is what passes through us. And in fact, we have to be as accurate as a bank in terms of money. Okay, so I've drawn you the technology. Let's talk about these two areas. So part of the technology is we have a load balancer, which is Nginx. And as I said, our smart throttler and the other portions of the high-speed area are written as Nginx modules, plugged into Nginx. So if you're a Lua guy or girl and you want to have an interesting job, come and join Adform. If you're a Lua person, by the way, I think you've got a sick mind. All right? Lua was one of those programming languages that people on drugs got together one weekend and invented. It's really powerful and really fast, but it's really weird. Then we have a bunch of bid servers. So once we filter out everything we don't want, we have a bunch of bid servers. We have between 102 and 105 of these things, and they're actually written in .NET. We sit there and we listen to those requests. Their job is, once we've got a bid that we're interested in responding in, to work out exactly how much we're prepared to pay and which creative, which ad, which advertiser we want to present. And we've got to do that in all of that stuff in 50 to 70 milliseconds. So how do we do this? We need a database. And the database is primary key type lookup all the way along. So we've got to be able to read the database in a millisecond or so, understand the cookie profile, and decide what to bid on. In fact, we do that 6 or 7 times. We go to the database 6 or 7 times. We started out with Cassandra for this because Cassandra was a very popular technology. In fact, it's a fun technology. I quite like Cassandra. But after 2 years of fighting with Cassandra and not being able to keep up our throughput rate, we moved to Aerospike. So Aerospike gives us it's a big key value store. So think of it as a hash map in Java or a .NET dictionary that's really, 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 really big in a distributed environment, distributed cluster. So we can read and write a particular record associated with a primary key in about a millisecond. The records are about 1K in size, so we still get good latency out of them. But we got 8 billion of these things. We do 800 to 900,000 reads in a second and about 100,000 writes in a second. So we've got more than 1 million operations per second on the database. And we need high availability. So Cassandra didn't give us the high availability because, Cassandra is written in Java, so it runs in a JVM. And every so often, the JVM is like your mother. It says, okay, put your toys away. I need to clean the floor. And you get up on the sofa with all your stuff. And she cleans, and she says, okay, you can go back, and you put your stuff back down and carry on what you're doing. So that's what garbage collection is like in a JVM. The other thing, too, is because we store 8 billion cookies, that's a lot of stuff. So we went from 150 Cassandra servers down to 8 Aerospike servers. So our DevOps people only have to worry about 8 things instead of 150. But we faced some problems. It was about a year ago, a little more than a year ago. The CEO and the CIO came into my office and went, okay, we have a problem. We're not being able to spend the advertisers' money fast enough, which makes them grumpy and we don't earn any money. And it had to do with the speed of our bid. So we could identify the user in a millisecond or two, but it was taking us too long to decide how much to bid and which creative to put in front of you. So we had a problem of high latency. The cause was .NET dictionaries. We'd built inside our bidders this structure made out of .NET dictionaries. It was essentially a bunch of filters. So if it's male, go this way. If it's interested in cats, go this way. If it's somebody who lives in Poland, go this way. So a set of filters, like predicate filters in an SQL statement. And we had got to the limit, the boundaries of the capabilities of the .NET dictionary. It's a great hash table, so I'm not saying it's bad at all, but we had just used it too far. So we were losing money, and we had to go back to computer science, right back to first principles. So I've got Donald Knuth's Art of Computer Programming up here. So we looked for algorithms that we could use. When we came up with a fixed length binary array, and we did a binary search in it, just like you did in like the second week of your computer science courses at university. And that solved the problem. But we did that, of course, in C, and that allowed us to do it very, very, very fast. Okay, so that's the money side of that. That's the exciting flow in. Data management platform is where we gather information from the internet and we process it into audiences. So first of all, you're all familiar with this page. This is the cookies page in Chrome, and you might find that you've got an ad form, track.adform.net cookie. You might find other things from people like DoubleClick or Google. There's always about 8 Google cookies that you've got there. And these are some of the things we use to track your behavior. You've been to a website, you've accepted the cookies, and we want to see what you're interested in doing. We don't care what it is that you're doing, so we're not the secret police or the Southern Baptist moral right. We don't care if you're looking at questionable websites that might end with hub or something like that. There's some smiles in the room. We just gather information about what you're interested in. We filter most of that stuff out. Our job is to take the cookies that we know about and group them into segments or audiences. So we have 5 billion cookies. Some of them have first-party information like the browser that was used, the language that it was, the location that it was in. Then we have cookie segment pairs, so we have 250 billion of these. 250 billion. Okay, that's a big number. If we all had if we had a 1 euro cent for that, we'd all be rich driving Teslas and flying to the moon or something. So we get, these are our traffics. You'll notice that we have a traffic map there that's gone up recently. We double every 6 months. And we have a lower cookie profile update. It's only about 100,000 a second. So that's when we are tracking what you do. We take all of those things and we analyze it and put it into an audience. So this complex picture over here, which I'm not going to elaborate, is the way our architecture works. We have a flow of real-time data come in, so we use a Kappa style of architecture. If you're not familiar with that, think of a log structured write where you're writing always at the end of the log very quickly, and it's an immutable record that you're writing. We have a Lambda type architecture that takes all of that stuff, not in real time, but in, if you're a Spark person, it's like Spark streaming. We process that, we decide where you are. But we use a a statistical approach to it. We couldn't actually do all of the numbers in the right amount of time. We have to use the statistical approach. We secure everything with OAuth 2, and we have a microservice architecture. I'll talk more about microservices in a minute. So, this is the technology that we use. The right tool for the right job. As you could understand, that might be fucking hard to keep track of. So we're trying to simplify it because not everybody has an Einstein brain. We have to keep track of it because we're humans that have real problems in our lives. We might be sick or hungover, or, you know, your partner has just got mad at you, so you're feeling terrible, or you're feeling arrogant. So we've got to reduce the number of technologies. So we're looking to get rid of a few of them out of our version 2. So we have some Java that we don't really need. We could do it all in Scala because we have Scala skills, Scala resources. We used MongoDB for an unknown reason. We don't actually need it, so we can reduce the level of technology. Just to take a few things down. There's nothing wrong with any of those technologies. It's just too many. All right. So, the biggest problem with DMP is that we have tons and tons of data that flows in. So this is the data pipeline that as a data science or a data engineer you have to process, and we have so much of it. That's the challenge we have. So one of the solutions that we do is we use probabilistic, I have trouble with English, it's my first language, probabilistic algorithms, and we monitor as much as possible. So the Grafana and graphite style of monitoring is absolutely essential for us to see how things are performing. Not just things like CPU utilization or disk usage, talking about the number of things processed in a second, and that makes sense. So there are two big parts of AdForm. 3/4 of our revenue comes through those high available, low latency, high throughput applications. DevOps. DevOps are the heroes, all right? They are the heroes. We might be the dreamers as programmers or architects, but DevOps are like Scotty on the Enterprise. He makes it go. So that's what happens with DevOps. We got a lot of servers. We got 1,600 servers last time I checked. Bare metal servers, physically in data centers. We use our own private cloud. We only use a public cloud in one place in the world. We use mostly CentOS as our Linux distribution, and we have some Windows requirements. So these are our data centers. So we've got one in Vilnius, 3 in Copenhagen. There they are in Copenhagen, woohoo. New York, Hong Kong, Singapore, and one in Sao Paulo, and another one that's probably going to go into San Francisco soon, next year. So we've got data all over the world. The data is almost the same, and we have to push the data around and maintain all of these machines. So our network is configured with dark fiber. So dark fiber is that special technology that breaks the speed of light. So there is negative latency inside dark fiber. I'm just kidding. It's really fast though. It's a lot of money, but if you need that low latency, it's astonishing to the point where it's faster than the old IBM channel-to-channel stuff in the mainframes, and you can have it distributed. It does cost a lot of money. It's not cheap. When we do provisioning, so this video on the right-hand side here, we use Foreman to provision up to the OS. Then we use Puppet to take over to provision each individual VM, and the orchestration for VM is done in Terraform. And this video you see running on the right-hand side, which is completely unreadable because of the pixels, is provisioning 100 VMs specifically using Terraform. So we make sure that the physical machine's operating system distribution and any virtual machines are the same. So that minimizes the number of things that our DevOps people have to deal with. So if somebody comes in and says, we want to use Ubuntu, the first question is why? We're using CentOS. Why do you want to use Ubuntu? If they say, because we like it, well, it's not a good enough reason. You might have a very logical reason for a new OS, but specifically we like to keep it as standard as possible. So inside our own data centers, we use OpenStack to build our own cloud. We use Ceph as our slow speed storage. So if you're not familiar with Ceph, it's essentially an implementation of S3 that you can use in your own private cloud. We have separate deployments, development, production, well, pre-production and production. In fact, we have 2 development environments. They're called Dev 1 and Dev 3. I don't know what Dev 2 was, but it's not there anymore, so it's gone. We have a nice self-service implementation so that if I want to spin up a VM to do something, then I can do it within boundaries without having DevOps involved. So if I want to test something, I can spin it up and it works. So coming in 2018, we're introducing both containers, so Docker and Kubernetes. So why would we introduce something like containers? Anybody got any idea? Why wouldn't we stick to VMs? It's more than that. It's fucking easier. It's insane to run a virtual machine on top of a physical machine when you don't need to. It's dumb to be running a Linux virtual machine on top of a real Linux operating system for no good reason. You're just wasting CPU cycles. And as a computer scientist, it's like having a rock in your shoe. You go, I can live with this, but gee, it's really annoying. I've got to get it out. Let me talk about .NET Core. Adform has a really big investment in .NET skills. A lot of our stuff is developed in .NET. .NET's not a bad environment to build in. In fact, it's quite mature, quite stable, got good resources backing it. So why .NET Core instead of just .NET? Just as I said, it's nuts to run a Windows VM on a Linux machine if you don't have to. It's insane. So we've jumped into the .NET Core pond in the shallow end. Our API gateway is written in it, and we've just done a new project which is a company-wide audit log. You know, you change a record, you want to know who changed it and what the change was. And we've done that in .NET Core quite successfully, and I'll show you some of the pain points in the next slide. But .NET Core is not .NET. So if you've done something cunning and you've made a Windows system call in your .NET Core code and you've forgotten about it, it's not going to work in .NET Core. So you just have to bear that in mind. So when we were building the audit log, I said to the guys, can you just tell me if it's too painful? If we get partway through into it, we get to some point in the project, we'll just go back to .NET. And so this is their actual notes. And so in a, 150 man-day project, we burnt about however many hours that adds up to. Little nitpicky, annoying things in .NET Core that haven't been polished off yet. So is the cost of doing these things worth being able to deploy on any platform? And the answer is probably yes. Okay. So what does it give us? It gives us platform-independent solutions. So, Windows, Linux, and something else that we haven't invented. So imagine we had to run something on a Raspberry Pi, for instance, like monitoring, not real-time bidding. We'd have to have like 1 million Raspberry Pis, but something else. So we can put some code on that thing. We have a bunch of brilliant software engineers, and we like to keep them. And as you know, when you're a software engineer and you're really deeply into a technology, learning a new technology is uncomfortable. You can actually do it quite well, but it's painful. You feel terrible for about 3 weeks. And we don't need to have everybody experts in everything. So we want to retain our engineering investment in that. And of course, it allows us to do containers, and containers allows us to be more slick in the way we operate. So essentially, if we can go to containers, we will reduce the number of physical machines we use, or reduce the resources on each physical machine, and therefore not have to buy any new ones. The idea is we want to save some money. Okay, so that's really cool. I've talked about real-time bidding, and I've talked about our DMP. and I've talked about .NET Core. Let's talk about data storage. So we have lots of data. So the first thing we do is we have a big HDFS cluster. So 2.5 petabytes, lots and lots of memory, nearly 10 terabytes of memory, and lots of cores, 2,800 cores to run on. So that's in the ETL cluster. That's where we take some data in, and we change it, and we put it out that side. In the DMP cluster, not quite as many, but still 1.1 petabytes. Anybody know how big a petabyte really is? Well, let me tell you. If you think of the book, the Bible, the King James version of the Bible, your grandmother probably had one. It was a big, thick book that was on her dresser or something like that. That's less than a megabyte of text. So a petabyte is fucking huge, okay? So we got lots of that. We use that a lot. What you put on top of HDFS depends upon how well you use it. So I'll talk about that right here. We used to do a lot of processing in Hive. And when I joined the company 2 years ago, I thought, really, Hive? It works. It gives you the right result, but maybe we should try Spark. So I convinced one of our ETL team to do the same thing in Spark. So Spark is about 30 times faster than the same processing in Hive, based upon our studies. And we went from using CSV files to Parquet, and we saved about 30% of disk space in it. So it was faster, and it took up less space. That means we can get the job done quicker. The cores that would be doing this processing are available to somebody else, and we can use our hardware more efficiently just by changing the software. Now, that's a really simple phrase, but changing from Hive to Spark means you have to invest some engineering time. Okay, so storage. If you have a column problem, a really big column problem, which is what we have, we use Vertica to do that. That gives us a scale-out, horizontally scalable column storage solution. So Vertica is a database, it's a column store. Really, really fast. So look at our Vertica. We've got 250 terabytes. Average latency is half a second, and we do about 30 to 40,000 requests per hour. Okay? With Aerospike, we're looking at a row problem. It's a row problem. It's a primary key looking at a particular value. So this we do about 1 million requests per second, and we want a latency of about 1 millisecond to do it. Two different types of problems. That's to solve the column problem. This is to solve the row problem. Why can't we do it in one database? Because there isn't one that does both yet. Okay, Kafka and Confluent. Kafka is our pal. So you can see here, these are messages by broker. We do about 1 million, I don't know, best way to describe it, about 1 million messages per second in Kafka. Kafka is our lifeblood. Everything goes into Kafka, everything comes out of Kafka. Big cluster, large amount of storage in it, almost as big as Vertica. And we're moving to Confluent. So if you're not sure what Confluent is, not to be confused with Confluence, the wiki tool. Confluent is the company who writes Kafka and is kind of a very grown-up way of using Kafka. So what was the impact on introducing Kafka? In the past, when you had your own integration, it would take about 3 months to implement. Today, all we have to do is to subscribe to a topic and we can get the data that we're interested in. Big difference. 3 months down to instantaneous. Okay, so I've talked about technology, and I've talked about AdForm, and I've talked about what we do. Now it's time to tell you, give you some Uncle Pete's advice. This is my kindly grandfatherly advice. If you have a data flow, data is the blood. Kafka is like the circulatory system, your veins and your arteries. And Confluent is like a healthy lifestyle. So you don't fill up your veins and arteries with fat and cholesterol. Confluent is the way to do it. So, storage and processing. If you've got a row problem and it's really big, use Aerospike. If you've got a column problem that's really big, use Vertica. If you've got raw data, use Parquet. You know, just don't have the argument, don't have the pub discussion, don't have the brawl in the stand-up meeting, just use Parquet. And if you can, use Spark instead of Hive, you'll get some gains. So that's Uncle Pete's first piece of advice. Technologies to watch. So, graphics processing units. So this is not a gaming system, but there are some technologies that go with them. One is Scream and MapD. They're column databases that give you phenomenal multi-filter queries with no indices on the columns. So phenomenal. They boast to be 100 times faster. They do both suffer from concurrency issues, but if you want to do queries, Scream and MapD. In fact, I can put you in touch with the right guy in Scream. I have another column database over here. This is ClickHouse. This is an open source database that is a great column database that could be a replacement for Vertica sometime in the future if we already hadn't spent a huge amount of money on a site license for Vertica. So ClickHouse is something to consider. Also in the GPU space is the deep learning. So something like TensorFlow and Theano. If you're going to run TensorFlow and you want to do it faster, all those little tensors get processed in thousands of GPU cores instead of CPU cores. The other thing here I've called persistent RAM. You have it both as DIMMs, non-volatile DIMMs, and SSDs. So the first instance of this is Intel Optane. Let me describe what this is. Instead of having a capacitor inside a chip in dynamic RAM or a floating gate MOSFET inside an SSD, this is a new technology. It's essentially like a resistor. It's persistent, but it's almost as fast as RAM. So imagine if you could have an SSD size storage that was as fast as RAM. Wouldn't that be interesting? In fact, you could, and it was persistent, you could eliminate the need for what we currently have as file systems or databases, because you would just have a process with lots and lots of RAM inside a machine, and you would never have to worry about it being powered down. So we're going back all the way back to the 1970s when core memory was the way you did things. Okay, so let me talk about open source and enterprise. There's a couple of religious fights about open source and enterprise, which is better. So open source doesn't equal free, but it's cheap. There is a cost associated with it. If you use open source, I recommend that you fork the repository yourself, download it, and know how to build it. So once every quarter, build those packages yourself. Because if the people who sponsor the open source go out of business, or don't want to do it anymore, or it becomes illegal, you aren't stuck. So you should be able to survive on your own if you need to with your open source. Pretty simple to do, not a big expense, but put it into your regular processing. Then you look at the enterprise side of things, it's value for money. You get some consulting and training, but you have a neck to choke. So, some years ago, Oracle bought Sun Microsystems. So everybody who had a contract with Sun Microsystems for Java now had a contract with Oracle. There was a legal obligation to do that. So that's what you get out of enterprise. At some point, you can cross the boundary between open source and enterprise, depending upon the economics of it. If you're employing too many people to maintain the open source, then perhaps you could save that cost and put it into buying the enterprise license. User process. So continuous integration, continuous deployment is probably a great idea. Have a blue-green deployment and feature toggling. So when you bring out a new feature, have a way in your code to switch it on or switch it off in case you've screwed up, which all of us do. Have a DevOps culture. So think about how this is going to run in production. Don't expect that you've got an infinitely fast CPU with an infinite amount of memory and infinite amount of storage. Think about humans are going to have to run this. I can't emphasize this too much, but hire good people. Good people are more valuable. 10 good people are more valuable than 100 stupid people. It just works better. So hire good people. If you haven't found the right person, continue to advertise. There will be somebody who can do the job. People are your best investment. In Adform here in Warsaw, we have a bunch of data scientists, data engineers, and the guys who do the front end of the Nginx. Very interesting work. So if you're interested in a job, use an agile process. So when I say an agile process, so agile process is a way of getting something done, getting the processing done, getting the project out. It's a great flexible technique. But agile is not an excuse for being bored or have a short attention span or wanting to touch the new shiny object. It's not a club, a social group, or a cult. So it's not a religion. You shouldn't have arguments in a stand-up meeting going, well, that's not an agile way of doing things. Okay, Murphy's Law. Anything you haven't tested for the last year will break, even if you haven't touched the code. It's called entropy, law of thermodynamics. So anything you haven't tested will break. Run your unit tests, run your integration tests, even if the test itself is 3 years old. You will break something. Okay, retrospectives and refactoring. There will be times when you screw up. Absolutely, totally screw up. So this is a time to go back and work out what you did wrong and refactor it. Get rid of the stuff that doesn't matter. Or build into your backlog times to refactor and test to take stuff out, because you might have technical debt in your code that you can remove. All right, avoid the superhero. This is the superhero. You've all been one, or you will have one in your teams. This is the guy or girl who knows everything, can get everything done. That's the person who troubleshoots everything, who holds it all together. The problem is they will go on vacation, or they'll have a baby, or they'll leave the company, or they'll get hit by a bus. Have two superheroes. Have a Batman and a Robin, so that, if Batman dies, Robin can step up and do the job. So don't rely on one person. There's nothing bad about it, having more than one superhero. Oftentimes, superheroes have a certain personality. You know what I'm saying? So you have to control that, manage that. All right. We're all a little stupid, but it's not a competition. Everybody does dumb things. The way to avoid your dumb thing finding its way into production, raise your hand if you put something stupid into production. Yeah, just, you don't want to talk about it too much. Is have a peer review, check with a colleague. I'm an architect, and I regularly wake up in the middle of the night and go, oh, is that a stupid idea? Who can I check this with? Because I might have this really cool idea, but it might be absolutely impractical. And, this is the book from O'Reilly there, hoping for the best, hoping this works. So just don't code it and throw it into production. Okay, some wisdom. The solution should be as simple as possible, but no simpler. So the lock on the bike is perfect. It's been implemented incorrectly. It's an operator error. This one is quite important too. A hypothesis is a statement whose truth is temporarily assumed to be correct, but whose meaning must be beyond all doubt. So if you come up with a great idea, you have to explain it completely to your colleagues, and then you can test it to see if it works. If you can't explain it, then it's not a good hypothesis. Okay, parallelism at every step. If you're not sure the difference between concurrency and parallelism, look at this graphic. Concurrency is where we're sharing one resource. Parallelism is where we're using more than one resource. So strive for parallelism at every step in the way you use your threads, your CPUs, your RAM, the I/O bus channels, the IRQs. Everything that you do should be as parallel as possible to achieve high load. And finally, Nothing beats running code. If you have a beautiful piece of code and it's you've got a great team spirit and you've worked with a great project methodology and it doesn't run in production, there's no value to it. So nothing beats running code. Okay, we've got a few minutes for questions. Who would like to ask me a question? Oh, don't be shy. Come on. What's an Australian doing in Europe? I moved from Silicon Valley to join Adform because Adform's a great company. What's another question? So how big is our DevOps team? Our DevOps team is really tiny. We have about 80 people. We have about 300 software engineers. And our DevOps team are very specialized, so it's quite small compared to the engineers. But they're the kind of DevOps people that are brilliant. So if I'll pick on Thomas. I work out that if Thomas had just had an argument with his wife, was hungover and had diarrhea, he could still get more work done than the average idiot that I find in Silicon Valley trying to do the same thing. And Thomas lives in Lithuania. So, yep. Yes, we do. I didn't discuss it today at all, but on the cell side, we have the cell side components of it. So Adform is complete. So we do all parts of ad tech. We're not specialized in any one place. So we do something on the, that's the publisher side, where the publisher says, I've got all these pages and I do this kind of stuff and I want to sell them. So we do stuff on the SSP side. I don't personally work with the SSP platform, but I have a good colleague who knows it backwards. Absolutely. Another architect. Okay. So the question is, how do we match a particular individual's cookie to something they're interested in? Well, first of all, things that you're interested in a year ago are not important because you're not interested in buying something today. So things that 3 months ago are marginally important, things in the last week are very important. So as we track your behavior through our data management platform, and based upon the data we may buy from someone else, we can then take your cookie and put you into several segments. And then we combine those segments. So the magic in doing that is done by the voodoo and black magic people in our company. So do you know who I'm talking about? The voodoo and black magic is done by data scientists. In fact, some of the guys in Warsaw do this black magic. You remember at university in that statistics subject you did in maths that you really weren't interested in and you only just wanted to pass? And you thought it was boring and you wanted to do computers instead? Well, that's what data scientists do, but they do it for a profession, and they discover the signal inside the noise. So you've got this big atmosphere of noise, and they find the little pieces of signal that fly through. So how we do it, I can't give you the specific details other than cunning, clever people smarter than me do it, based upon your internet behavior. Any other questions? We have shared data centers, so we don't buy a physical building and provision it ourselves. So we use bare metal data center providers, and they give us essentially racks, power, and a big connection to the internet. And that's all they give us. And then we actually physically have guys and girls who go round to all of these places and install the stuff that we get from HP and put the drives in and move DIMM modules around. Okay, so the question is, how do we build a cookie database? Because we do all of ad tech, our publishers give us permission to put tracking points on their website, tracking pixels or cookies, the like sort of things. So that's part of it. On the buy side, once we place an ad, we have the right to track the behavior associated with the ad, so that if you look at the ad, whether you touch the ad, all of these tracking pieces of information come to us. And then, of course, we buy data from other people. So surprisingly enough, we buy data from Google. People like Uber or anybody who tracks first-party data about yourself always want to sell that data. So we take that data and process it. So it's partly from what we record ourselves and partly what we've purchased from someone else. Yeah, that's right. So what happens is the data scientists put on the hood and the cloak, and they stand around in a circle and they chant to each other, and then they come up with an algorithm somehow by putting, you know, eye of newt and tongue of frog into a big cauldron, and they come up with the answer, and then us humble engineers go, okay, well, we can implement this by doing this. Correct, we do. So it's a statistical approach or a probabilistic approach to do it. Specifically, what we've just worked on is matching not only the cookie, but if you have a device, you know, an advertising ID in your phone or something like that, and you've been looking at cars at home on your computer, and you're looking at cars on the way to work on the metro, we have a cross-device mapping technique as well, and we verify by statistical means whether we're accurate or not. We're probably about 85% accurate, but there's always that gap where, you know, your daughter or your son was looking at something, or your boyfriend or your girlfriend or your wife or your husband was looking at something, and then you're specifically looking at high-speed racing cars or something like that. So. Correct. We have some capability to do that within the boundaries of the laws that are set in the EU and in the other countries we work in. In fact, we expunge any information from our databases that are too personal. Like if we somehow got your email address or somehow got your physical address, we go through and we expunge that to be compliant. All right, one more question and then we'll finish. Yep. Okay, so we have an excessive capacity already, and we share that excessive capacity from our production. It's available to the production environment as priority. Then it's available to development as a lower priority. So we may sacrifice pieces of our development capacity for production spikes. All right, well, thank you very much. Appreciate it.